Week 7, Video 3, Derivatives from First Principles. So the process where we find the gradient of the curve is called differentiation. And our gradient function is called the derivative. So to properly define the gradient for a function, we need to find a formula for the gradient of the tangent to its curve. So the derivative of a function y equals f of x at a given point px, y, is the gradient or slope of the function at that point. To use first principles to find our derivative, we're looking at going back to our original concepts of our change in y on our change in x there. So we start with our point P, x, y here, or x, fx, depending on what terminology we're using. Then we draw segments from a point P to others on the point, say Q1, Q2, with Q points getting closer and closer to P. Let the point Q be where the horizontal distance from P is small, and this is our change in x, delta x. The y value of Q will similarly be a small amount. We're going to call this our function of x plus delta x here. So here, because we're not looking at our delta y, we're looking at here our function of x plus delta x here. We're adding that small amount in here, and our x here is our delta x. So our point Q has our coordinates x plus the change in x, delta x, y plus change in y, delta y. So if we look here, our point P here has our points x and y. So P is x and y here. Oh, sorry, f of x here. X and f of x here. Our point Q, we have x plus delta x and x plus delta x on both sides. So our change in y becomes our f of x plus delta x minus our f of x. So we're looking at this difference in here. This one minus this one gives us our change. And here again with our x's, we're looking at the difference. Our x plus our delta x, change in x, minus the x here. So if we go through this and we substitute out here, we can get rid of our x minus x. So we have our function of x plus delta x minus our function of x divided by delta x. As delta x approaches 0, our point Q approaches the point P. So here, as our change in x gets smaller and smaller and smaller, our change in y will do the same as well. So we've got to try and have a little bit of space. Mathematically, we say as delta x approaches 0, Q approaches P here. We're going to be on top of this point here. Therefore, the line becomes a tangent at P. We call the gradient or slope of this line the derivative at P. So we want to find here the derivative of y is equal to x squared plus 3 from first principles. So our formula for our derivative, we'll write that down first. dy on dx is our limit. As x approaches 0, our function of x plus delta x minus our function of x divided by delta x here. So we substitute in here. Here our limit as x approaches 0, here we're going to substitute in our formula x squared plus 3. So here we're putting x plus delta x in for our x and then squared plus 3 minus our function of x here, x squared plus 3 here, divided by delta x here. So our limit as x approaches 0, and we can work through this here. So we end up with here x squared plus 2x delta x plus delta x squared plus 3 minus x squared minus 3 divided by delta x here. So we 3 minus 3 deletes out here, x squared minus x squared deletes out here. So our limit as x approaches 0 becomes 2x delta x plus delta x squared divided by delta x. If we look at the top of our equation here, we see we can take delta x out. So our limit as x approaches 0 of delta x outside of 2x plus delta x divided by delta x here. We can cancel these out. Becomes our limit as x approaches 0 of 2x plus delta x here. And so here we're saying, we substitute in here, we've got is equal to 2x as x approaches 0, as our delta x approaches 0 here. So next we want to find the derivative of y is equal to 2x from first principles here. So dy on dx is our limit. X approaches 0 here. The function of x delta x minus our function of x divided by delta x is our limit of x going to 0 here. 2 side of we got x plus delta x here divided by delta x is our limit here. Delta x approaches 0 is 2 delta x divided by delta x. Here we keep on going, we've got here delta x divided by delta x divide here, it will be limit delta x approaches 0 of 2. And so here our derivative will be 2. So looking next at continuity. A function y is function of x here is said to be continuous at y is equal to c, so at this point when y is equal to c, when the following three statements are all true. So y is a function of c exists. So that's our first thing we need to look at. Is it actually true at that point? We have a limit as x approaches c for our function of x exists. And here if our limit of our function of x is equal to our function of c here. So we want to see is y equal to 2x continuous at x equals 2 here. So for our test 1 here, we say, well, here f of c. So that is x, or is it equal to c here. So we want our function of 2 here. So here 2 times 2 is equal to 4. So here y is a function of c exists. For 2, we have a limit x approaches 2 of our function of x here. So our limit x approaches 2 is equal to 2x, we substitute in, is equal to 4, and that exists. For 3, we're checking that our limit here, function of x as x approaches c, is equal to our function of c, which we had here. And both of those are equal to 4. So our limit x approaches 2 of our function of x is equal to our function of 2 here, or function of x there, c. Here, so this is true. They're both equal to 4. So we say, therefore, function y is equal to 2x is continuous at the point x is equal to 2.